Welcome to the 23rd video on Introduction to Quantum Field Theory. In this video, we will be talking about the Procca equation and its solutions, mostly about what the polarization does, and like for direct spinor, showing that the components satisfy the Klein-Gordon equation. To better understand the structure of these solutions, however, it is useful to first take the divergence of both sides of the Procca equation. So if we come up here to the Procca equation, let's just copy it, just paste it here, and then we take the divergence of both sides. So that means going partial beta, partial alpha, f alpha beta equals, then there's not going to be any change because this is a constant, and then you have partial beta, a beta. The left-hand side, which if you're familiar from classical mechanics, the left-hand side here will go to 0. So this term is 0. So this implies that 0 is equal to negative m squared partial beta a beta, which implies that partial beta a beta equals 0. And this right here, this is the Lorentz condition. No, not Lorentz. Lorenz, if I can spell. Lorenz condition. And the Lorenz condition basically is just a statement that the time-like component minus all the space-like components partial 3, a3, all of this is equal to 0, which this right here, if we just put it in traditional vector notation, this right here is the Lorenz condition. This quantity represents the divergence. So if you have the amount of some like substance coming out, so like if you imagine that this A is, if you imagine this vector field A is changing at a point, um, and there's divergence there, then the way that this changes in time is fully determined by the flux in and out of a little bubble. And so you can imagine this A beta, this 4 vector, as some kind of like almost like a fluid that exists. That me putting it in those words will be controversial for the way that modern physics is presented. I don't think it should be, because in reality, like it's not saying that there's like a physical fluid in the sense of like a particulate fluid, but it's saying more so that this 4 vector potential, this gauge field behaves like a fluid. And so if you imagine a fluid, if you have a certain amount of fluid leaving a little bubble, then that tells you how the fluid is changing in time. So that's the same thing going on here. And that's what the Lorenz condition says. And we can use this condition to simplify the Procca equation. We can use the Lorenz condition to simplify the Procca equation. So if we have negative m squared a beta equals partial alpha f alpha beta. Remember from the last video and from other videos that we have that this anti-commutation right here is the definition of F. I think I must give it somewhere up here. I guess I don't. I guess I don't. But this quantity right here is equal to F. So let's copy this. You can put partial alpha, then put that in there. I've been listening to the Gladiator soundtrack while I do all my notes, and so it's stuck in my head. Like the We Are Now Free song is now stuck in my head. Anyway, we can expand this. Partial beta, A alpha minus, oh, hang on. Wait. This is, it's actually this. Okay, I should have just stuck to my notes instead of copying and pasting. I used slightly different, I used a different sign convention there, so let's just continue. This is actually what it is. And you get this and beta, then partial alpha, partial beta, A alpha. This will be the same. And then you can rearrange these. So you can say partial beta, partial alpha, A alpha. And then this is the Lorentz condition. So this goes to 0. So we just get partial alpha, A beta. And this is because of the Lorentz condition equals 0. Therefore, we have partial alpha, A beta equals minus m squared A beta. And this is the simplified version of the Proca equation. And this, of course, is a wave equation. Wave equation. And this tells us that each component of A beta satisfies the Klein-Gordon equation. So recall the ansatz for the gauge field. That is this A mu x mu equals F of x mu epsilon mu, where epsilon mu is the polarization and F of x mu is the space-time structure. We can plug this into this wave equation. So we plug this into this. So we get, therefore, partial alpha of A beta x mu is equal to partial alpha of F of x mu epsilon mu partial alpha And then the F mu, recall that this is the I K mu X mu, and then we just have epsilon mu here. Except this epsilon mu actually doesn't change with space, so it's going to be independent. All the derivatives will not affect it. So the derivatives will only affect this quantity here. Well, taking the derivative, first we get an I and then a K and an alpha down here. Oh, and I keep writing, I made this mistake in my notes and then I had to go correct it. This right here should be a beta. Yeah. And then, so we get, well, I K alpha, partial alpha of e to the I K mu X mu epsilon beta, which just gives an I squared K alpha e to the I K mu X mu epsilon beta. And what this implies is that, and then recall that this is equal to negative m squared, all of this. And the negative m squared comes from this. Oh, don't know why I did that. Comes from this. So you put the negative m squared. So you can see that k mu, k mu, and I'm just relabeling these alphas into mu's here, is equal to m squared. So we get the mass shell condition slash dispersion relation. Again, who would have thunk that wave-like structures have the mass shell condition in physics? Who would have known? We didn't see this coming. Anyway, this doesn't tell us anything new about the structure of wave-like um, objects. So we need to look at something else if we want to learn anything new about the solutions to Procca equations. So we need to look at the Lorentz condition. That will tell us something new about the polarizations of the Procca equation solutions. So we must use the Lorentz condition to poke and prod at what these solutions are. So the Procca or the Lorentz condition is such partial alpha of e to the I K mu X mu epsilon alpha. Move this here so it's in the middle. And that's going to give I K, yes, I K alpha. And then there's going to be e to the I K mu X mu epsilon alpha. Now, because this whole equation here is equal to 0, this is constant, this is constant. These mu's are constant because they don't interact with these alphas. And this I is also a constant because it's, by definition, a constant. So we can divide out by these. We can divide those, and we just end up with K alpha epsilon alpha. Otherwise, the inner product between the basis vector or the polarization basis vector and the what do you call it? The wave vector. So this tells us that we have K naught epsilon naught, which we can just lower, and then we have plus K j epsilon j, which we can just lower, and put a minus sign here. And this is just k naught epsilon naught minus k1 epsilon 1 minus k2 epsilon 2 minus k3. And that's not an e, that's an epsilon 3. And this is the, novel information that this gauge field, which is a vector field, has components of, what do you call it? Has the, or it basically it tells us the polarization, how you actually describe wave vectors in the basis of the gauge field. So let's see what happens. Let's see what this means for a field excitation traveling in the z direction. So if it's traveling in the z direction, then that tells us that the um, k k1 k1 equals k2 equals 0, and k3 equals kz. So this implies that if we look at the mass shell condition, we now have this again. Well, because this is just a sum, right? And these are going to be 0. So we just have k naught squared minus k z squared. Now this implies that k naught, so we can subtract this over to the other side and then take a square root. So k naught is equal to the square root of m squared plus kz squared. So the new thing about the Proca equation is that if we have an object moving in the z direction, the time-like component actually depends upon it. Of course, and then if the mass is 0, then they're actually equal, and that's where we get the whole light-like vectors, blah, 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 that we've discussed many times. So let's see how this looks when we plug it into this. So we can say, therefore, epsilon mu k mu is equal to k naught epsilon naught minus, or rather, it would be it'd be k, what do you call it? Kz epsilon 3. Which will correspond to the following vector. Corresponds to this. Didn't change colors. So L means longitudinal. And then there's a normalization factor. We'll see why that comes in a second. And then square root of m squared plus kz squared. And then we can have 0, 0, kz right here. So you might be wondering why I don't have a negative sign here. And that's because I'm defining the basis of this to kind of like include the negative sign, which is a little confusing, but we'll see how it works as we continue to use it more. It's one of those things you just kind of have to get used to. Which is one of the reasons why I dislike tensors. Are they're cool. Tensors are cool. It's just I don't know. You can do all of this in geometric algebra, and it's much better. Okay, so you get this, and the normalization factor um, basically enables this to be normalized. So epsilon naught L L minus um, minus the 3 E3 L L, which if you have the 1 over m, this gets squared. It's the normalization constant. Then you get the square of the square root of m squared. So you just get m squared plus kz squared. Then minus kz squared. And this is just equal to 1 over m squared, which is equal to 1. So this is a normalization factor. And now let's consider the case that, let's say that kz is 0. So then if the field excitation, the field excitation is at rest, then let's put it this way, the field excitation is at rest, then kz equals 0, which implies that this polarization here is just 1 like this. So, and we've seen this in geometric algebra and other things. If something's at rest, then all of its spatial components are 0. And that's, what do you call it? All of the spatial components are 0, and then the time-like components non-zero.